Alright, so in this third part of this, I guess, mini-series, I guess is what you can call it, of the calculus in motion, we want to just continue working on some practice problems of common motion problems you might see in a typical calculus class. So this is one of them, and I just broke it down into several parts. We're just going to look at it one part at a time. So I have part A here. So let me just read the initial setup. A particle moves along a line so that its position for t is greater than 0 is given as this. So this is the important part, right? The position, this is where we'll be able to find everything. Assume s is in meters, so the position is in meters, and t is in seconds. This is a no calculator problem, so try to not use a calculator. If they do, then I'll tell you how you can use the calculator to benefit you, but I'm going to be solving it without a calculator. So we have part A. Find the initial position and velocity. This one's a very simple one because all we have to do is find the position at time equals 0. Looking at the function, every term except for the last one have a t in it, so they all are 0 except for the last term, so it's -9. Units of meters. Now what's the velocity? We want to find the velocity function first. And if you remember, it's just the derivative of position. We can use the power rule to find a derivative. 24t plus 36. Not too difficult, and then we just plug in v0. 0, which is equal to, this has all t's except for the last one, so that's 36 meters per second. Not a difficult problem, not a difficult part, so let's work on the next part. Alright, this is the second part. This is actually the part I feel like a lot of people don't like doing, especially without a calculator. If you do have a calculator, what I would suggest is plugging in the velocity function into your calculator and seeing when the value is positive and when it's negative, and that's where you'll find your time intervals where that happens. But we're going to try it without a calculator because I guess why not, right? Let's see. I guess when is the particle moving? Right, left, not moving. I guess the easiest of these is actually not moving, and we can do that pretty simply. Let's do this. So let me just write some notes off to the side actually. So when it's not moving, v has to be equal to 0. When it's moving right, v has to be positive, right? In other words, we can say v is greater than 0. And when it's less than 0, it's negative, it's moving left, right? Left is negative, right is positive. 0 is not moving at all. So we're going to do not moving first, since it's probably the easiest to set up. So we set this equal to 0. 0 equals 3t squared minus 24t plus 36. And now we have a quadratic set equal to 0. I'm thinking about factoring. I'm thinking about, yeah, definitely factoring. The quadratic formula is too much, especially without a calculator. So let's try, all these have a factor of 3, so I can just take that out, right? Divide everything by 3 just to simplify it. T squared minus 8t plus 12. Alright, so we're here. Alright, so let's factor this. So I'm just going to show you the factoring. Two factors that multiply into 12 but add into -8. Looks like it's 6, 2, and you have to make them both negative. Not too difficult. So I'm going to rewrite it as this. T minus 2 and t minus 6 equals 0. So that means t equals 2 and 6 are when the velocity is 0. In other words, at time equals 2 and time equals 6, the particle is not moving. So that's really helpful. So I'm going to drag this down a little bit. So we can still find the when it's not moving using a calculator, without using a calculator, right? With a calculator, what you would do is just plug in v of t and use the calculator to find the zeros of the function, and that's just, you can find that super quickly. But without a calculator, you probably have to factor. Let's move on to this part. So I'm going to erase this, but I'm going to keep 2 and 6 for a special reason, and show you why it's better to do the not moving part first. So let me move this up. Let's move it here. At t equals, let me just be clear. v of t equals 0. So let's look at this. Let's say 2 is here, 6 is here. I'm just choosing arbitrary points, right? So remember when something's positive, it's moving right, and when it's negative, it's moving left, right? And then think about this. I'm just going to draw a random parabola. It doesn't have to be exactly what this one is, but it might look something like this, for example. I don't think it's the one that matches us. It might be different. So looking at this, let's say this is the velocity time graph. Actually, let me just draw it here, just a little bit more right, just to show something. When it is positive, it is moving right. When it's negative, it is moving left. The positive values are all the way up here, right? So any t here is when it's positive. And then on the other half of the thing, this is when it's moving left, this section, right? Anything in the negative, right? Let me change this back to yellow. So notice how the parabola, this one that I drew, is divided into 3 segments, right? A positive, and then a negative, and a positive, and then the zeros, right here and right here. This is exactly, maybe, possibly what this is. So how do we know if a whole section is, if we know one point is negative, we know the whole section from the 0 to the 0 is in fact negative, right? If we know one section is positive here, then we know that this chunk or this segment is positive. So that's what we're going to take advantage of. How do we do that, right? So we have this velocity function right here, and we have the zeros. So let's try to take a point here, take a point here, and take a point here, right? Any point you like. And test them out. Test them out. V of 0. Usually 0 is the most obvious one, right? So if I plug in the V of 0, it's 36. It's positive, so I'm going to write positive here. And I'm going to color code it yellow, because that just reminds us of yellow. So now, what about somewhere between 2 and 6? I want to take a value. Let's just do, what, 3? 3 might be good enough. 3 times 3 squared, which is 9. Let me just, 9 minus 24 times 3, that is 72, plus 36. That is, let's do this, 27. Let's see, 27 minus 72, what is that? What is that? That is a negative 45 plus 36, which is equal to negative 9. So this is a negative value. And I'm going to color code this green to remind us that it's a green, right? And then finally, something bigger than 6. I like to do, let's do 7. 7 is fine. Yeah, 7 is fine. So you can choose any value bigger than 6 in reality, but maybe you find this easier to think about. 7. Let's do it. 3 to the 49, 3 times 49 minus 24 times 29 plus 36, or not 29, 7. This is 7. Why did I think 29 at all? Right, so 3 times 49 minus 24 times 7 plus 36. We know that, let's see, just an estimate. We don't really care about the value. We can just, if you really don't know the value, you can just estimate it, right? We only care about the sign, not the value. So this is like in 120-ish, 120 land. This is kind of like 140. Then this is like 35, right? If we add them all together, it looks like we're getting a positive number. And we are. I think it's 15 is what it actually comes into. But we just care about the sign. It's positive. Positive. Woo. So we're basically done with the problem. So here, let me erase all this work and just do up here. Let's look at the problem one more time. So, oh, did not want to, I just want to scroll it up a little bit. right about here. Perfect. So what we did was we took the derivative of the position function and we found the zeros, and we found where it's negative and positive by taking the test point, right? I used this argument where there's sections that are negative and then a section that are positive that are between zeros or after or before zeros. So that's the argument you can use, especially with polynomials. Polynomials are like that. If you did a lot of study of polynomials, maybe in pre-calculus, maybe you've understood the shapes and behaviors of polynomials, and you'll just know that fact. So now we have what? We have these values, right? What does this tell us? It tells us this section is moving right, this section is moving left, this section is just moving right. So how do we show that in terms of math, right? So when is v positive? It is positive for t goes to 0, right? It's positive at 0. It keeps being positive until 2. Is it positive at directly 2? No, so we have to put a parentheses, right? And then it is also positive, so this is a union, or if you want to just say this and, right? This is another thing of this and. It's not positive directly at 6, but anytime after 6. And it's positive the rest of the time. So this is, I guess, the formal way of writing it. So when is v less than 0, right? And that's just the middle section. So it is not positive at 2 or 6, but it's just anything between there. And then when is v equals 0? It is v equals 0, t equals 2, 6, right? So this is definitely one of the problems people don't like, but if you just take your time and look through it, maybe if you go through this process a couple times, it'll make more sense to you, right? So we'll be doing one more part. One more. Alright, this last part, we want to look at the acceleration, right? We spent the first one looking at the position, stuff about position, and maybe some velocity. The second part, part B, we looked a lot about velocity, and now this part we're looking at the acceleration. So, what is the acceleration of the particle at 3 seconds? Is it speeding up or is it slowing down? So, from the position function, we take the derivative, we get 3t squared minus 24t, right? We've done this many times in this problem already. If we take the derivative of velocity, we get the acceleration, which is 6t minus 24, right? Power rule. So what is the acceleration at t equals 3? Is it speeding up or slowing down? So we just simply plug in 3, right? We get 18 minus 24 equals negative 6. However, we're not done here. We are not done here. A lot of people get confused on what the meaning of acceleration actually is, right? So it's a kind of abstract concept, but just know this is the fact. Ready? Here, should be probably written down. If A is positive, so the acceleration positive and the velocity is positive, it's getting faster, right? This means getting faster. When they are in opposite signs, so there are two examples of this, right? These two are opposite signs, these two. So these two, getting slower. I would remember this fact because it might confuse you, because acceleration is kind of confusing for a lot of people. So we found the acceleration is negative 6, so we want to actually also find the velocity at negative 6. So the velocity at the velocity at time equals 3 is, what is it? It's 3 times 3 squared minus 24, 36, and this is what, 27, I think we did this one, 72 plus 36, and I remember this being negative 9 from the previous problem. Negative 9. Notice that they are both pointing in the same direction, right? They're both pointing in the same direction, so that means it is speeding up because they're pointing in the same direction, right? So every second it's going to speed up, right? Speed is just a sign of it, not the direction. So just keep this in mind. Speeding up and slowing down, and velocity and acceleration, they have to point in the same direction to speed up. If they're pointing in opposing directions, they are slowing down. So that's it for this problem. I know it's a lot, but hopefully these problems made more sense, and maybe you can try doing some of these on your own. So